All right, team. Cell potential and free energy. Here we go. The math in this section is fairly straightforward and easy. You have to do practice to be able to have it make sense, though. You can calculate voltage with this equation. The voltage, the standard potential. You're going to see this word, standard potential. It's not scary. It just means voltage, and they want you to be able to go like, okay, the voltage of the cell is equal to whatever is being reduced, which in this case, or the reduction, we've got the cathode, copper, minus the standard potential of zinc. And it's that simple. And so then you're like, okay, so the standard potential of zinc is, okay, and now you have to go, okay, so put these values in. 0.34 minus negative 0.76. The double negative is going to cause them to be added together. That magic is really important for you to note, and then you're going to have this value at the end. It's so important to practice these problems a few times because almost everyone makes mistakes on these problems. It's good to learn how to see these problems so you don't make those mistakes on the exam. Okay, here we go. We got standard potential of free energy in K. We have already worked with this guy on the right. We've done this earlier this unit. Okay, we were able to calculate K because delta G is an equilibrium, and we learned how to manipulate this earlier in Unit 9. Okay? But now we're going to say, okay, what if I have my voltage, okay, and the number of electrons that are reacting, which is right there, and then we have this constant, which is Faraday's constant. Faraday's constant comes out to 96,000, okay, 485. And that number is given to us on our equation C, so you don't have to remember that one. You just need to know where to look for it. Okay, 96,485 is what Faraday's constant is. And these math is some of my favorite of the year because it's so easy. It's just simple multiplication. Team, I don't want you to stress about units because if you just know to put the numbers there, multiply them together, you're going to end up with the answer that you need. So let's rock and roll. N is the moles of electrons that are reacting. Faraday is the constant, and then we've got our voltage. Make sure that you divide your answers by 1,000. That is a spot that's heartbreaking to lose a point or lose points. Remember, everything that we're doing is in joules. Okay, we've got this guy over here. We've got joules right there. This R value is always in joules. Okay, we come over here. We're working in coulombs, which means that when we finish this equation, this answer is going to be in joules. Okay, and so in order to be able to go from joules to kilojoules, we have to divide by 1,000, and then we are over in our kilojoules. All right, so let's get out of here. Let's rock and roll to the next slide. So, for instance, if I have this equation right here, calculating the free energy and K, first step is we just need to plug our numbers in. I have 3 electrons reacting here, and I can see that. I can see we won't go here to a 3 plus, that's 3 electrons. We started out here with a 1 plus, and there's 3 of them, and then there we go, we got to our solid. There's 3 electrons involved, 3 moles of electrons reacting. So I got 3 for my N. Faraday's constant, I've already given it to you, 1.54. You're going to get a nice big negative delta G. Okay? After you found your negative delta G, this delta G value, you can plug it back in to this equation to be able to find K. And if you don't know how to do that, go back to the last section, watch the video on how to do it, and as a quick reminder on how to calculate your K. With a negative delta G, anytime that I've got a positive E value, is the reaction thermodynamically favored? Yes, it is. Okay, so, and why? Here we go, let's turn this on. Negative N, okay, times Faraday, which is always 96,485, with times a positive is going to give me a negative at the end. So yes, it is thermodynamically favored. Yes, it is. I'm going to just do a Y there. Would you suggest the equilibrium has gone to completion? So depending on what my K value is, if I get a big old K, and I'm going to predict that this is that case, if K is a big old number, okay? If I got a big old K, okay? Sorry, I'm drawing here with a mouse. That means that, yes, it has gone all the way to completion. It's not really in equilibrium. It's pretty much gone to completion. So that's really important to note. Let's keep going. Free energy voltage and K values. If you have a negative voltage, what will the sign of my delta G have? Let's see here. So let's go delta G. Okay. Well, let's just go back in time so you guys aren't having to watch me draw painfully here. Let's just go back. Let's go back to this equation. All right. So let's pretend that our E is a negative voltage. And then I'm going to have a negative times a positive times a negative is going to give me a positive delta G. So let's go to the end there and ask the question, if I have a negative voltage, what will my sign? It's going to become positive. And if it's positive, then it won't be thermodynamically favored. No, it's not going to go to the right. It's probably going to be going to the left. Okay? And if my reaction is headed to the left, K is going to be small. And if a reaction is thermodynamically favored, what sign does the voltage have? That voltage always is going to be positive if it's going to be thermodynamically favored. The sign is going to be negative for delta G. K is likely going to be greater than 1 if a reaction is thermodynamically favored. This is important for you to wrap your head around. Some people will put this into a little table. They'll write this in a quick and easy way to be able to remember these based on this equation right back here, to be able to go look at this equation and be like, okay, what's happening? What's going to happen to K? What's going to happen to delta G? What's the story here based on my different variables? Important skill to have. I wish you success. Team, you've got this.